Okay, let's continue. So brittle material is not good for building, or because in sudden fracture. Ductile material is better. Let's go back to the. So now I will explain why this is a brittle material or why is a ductile material. When we talking about ductile, we should know what is ductile. What is ductile? What is the ductility? When we talking about ductility, there is a very important theory called dislocation theory. What is dislocation theory? You need to please follow me to write down the dislocation theory. What is dislocation theory? I need to tell you that actually inside a metal, it is a metal, is the dimension of 1 meter. When you enlarge the size, look into the particle here, maybe to the dimension of the 10 minus 5 meter. It's a very very small area, and you will look. There are many grains in the metal. There are many grains, and you keep going to look inside. You will find that actually in the steel there are many atoms get together. The atoms. So the atom structure in the dimension of 10 minus 8 meter, very near 1 nanometer, because 1 nanometer is 10 minus 9, so it's a 10 nanometer. So in the very small scale, and you can look inside the metal. Actually, there are many atoms. So in this case, one should know it's a very small dimension. That means 10 minus 8 meter is a very small dimension. You try to I ask you a question about this. Please write down, follow me. This one structure, another is this kind of structure. If this is atoms, now we may look bigger. Should be the atom here. You can follow me to draw on your paper. There are many atoms. There are many atoms here. So this is atoms. And also there are many atoms. There are also many atoms here. Okay, we call this model is a perfect model. Perfect model. And this is the defect model. Defect. That means there is a defect here. That means the atom is not continue here. Is a defect. Sorry, defect should be erased. Defect. There's some defect here. So we call this a perfect model. And this is a defect model. Yeah. Why we will propose two models? One is a perfect model, another is a defect model, because it's a very small dimension. Nobody knows the actual atom arrangements inside the material because very small area. Nobody knows. So the scientist should be proposed two different kind of model. One is a perfect model, another is some defect model. Because they think there must in some defect in the metal. The defect is the atom not continuing here. So we call this is the defect model. Okay. So now we will do a test. Maybe we will do a test here. Yeah, we'll test. The scientists, they'll do a test. The test will be sigma. Sorry. It's better for use loading. The mark is loading better. There is a parallel P here. And we will discuss a very important if the atoms suggest by a say is a normal stress. We say sigma n is a normal stress. And also maybe they will take a shearing stress. We call it sigma s, shearing stress. And when we under the perfect model should be all the bond should be break I mean, the bond should be break the bond. And it will fail. And in this case, everybody should know. In this case, it's better to use the color here. It's a dot line. It's a dot line here. Yeah. I think it's better to use this color. Yeah. We call this is a not break the bond, it's a change the bond. That means change the bond by shearing stress, and break the bond by normal stress. We have two different kind of model. So the conclusion is, when you use a perfect model, the yielding strength of perfect model is a near 5 times 50 times of 50 times of the yielding strength of test. That means when we use the model, perfect model, you will overestimate the yielding stress and more than 50%, 50 times. So this model is not good. But when we use the defect model, the yielding strength of the defect model the scientist very surprised when we use the model. It's very near the test result. That means it is very good assumption. That means it's a very interesting. Most of the metal inside is a defect. It's not continuous. The atom here is not continuous because under this assumption, when we do the theoretical calculation, and we can get the result very near the real test. So it's a very exciting result. So from many years ago, most of the scientists agree the model. Until now, we have some high technology machine. We already approved the inside of the metal is a defect model, not a perfect model. Now we already have the SEM, very high technology microscope. We can look the atoms is really look like this. So we call this is a kind of a dislocation theory. Let's go back to the So the dislocation, the meaning is inside the metal. Inside the metal, you will look the atom not continuous, so we call this a defect. And when you subject by shearing stress, the defect will from here move to here and then move to here. That means the bond will change. This bond will change to here. Bond change to here, and the bond change to here, and the bond change to here. So we'll go like this. So finally, the defect will move to another place. So we call this is a dislocation motion. Dislocation motion. This is a dislocation because it's used by shearing stress to change the bond. The bond is changed, not the bond, not the break all the bond, just change the bond. Just change the bond. So we call this a dislocation motion. It looks like this. This is change the bond. Change the bond, and the originally defect here and change to here because the bond change. So that means when we the idea when we break the bond, you need a lot of energy. So the value is very so high. So it's not near the real situation because you need to break all the bond. You need a lot of energy. But in this case, you don't need break the bond. You don't need break the bond. You just change the bond. So change one bond, a very little energy. But break the bond, break all the bond, you need a lot of energy. And if you only change the bond, you don't need a lot of energy. That's why it's very near the real test. But when this is the perfect model, you need to break the bond, you need a lot of energy. So after calculation is a very big value, more than 50 times of a real test. So now all the scientists say it's not inside the material, not this, is this. That's why everybody already, all the scientists agree there is a defect inside the material, And this is my student. We do animation. It's wonderful to explain. You see, this is look like a defect here. The bond change, so looks like the defect will move. We call this dislocation motion. Dislocation motion from here and to go here, from here to here. Just the bond change. And how to so this is applied by shearing strength. The shearing strength can change the bond. And also, it looks like the move of this kind of animal. I think everybody know this kind of animal before. Like a snake. You see, is a shearing stress, so the defect will move due to the shearing strength. It's a shearing strength. So inside the material, the shearing strength will let the defect motion. We call it a dislocation motion.